Hello and welcome to another edition of Teradata TechBytes. My name is Alexander Kolovos and I'm an analytic architect from Teradata's product development organization. Today we're going to talk about how Teradata's Vantage platform supports the Python language for data science and analytics. This is the fifth of a 5-part TechBytes series on this topic, which will provide you with an in-depth demonstration of how Vantage table operators support Python. My co-host for the series is Tim Miller, a member of Teradata's Technology and Innovation Office. First, let's talk about the assumptions being made regarding the content of this TechByte, as well as the key takeaways we hope all listeners will walk away with. There are two other parts of the TechByte series that should be viewed prior to this episode, namely Part 1, the overview, and Part 3, the Teradata ML demo. The key takeaways from this TechByte include how to use the script table operator to execute Python directly on Vantage systems, how to score models built outside of the Vantage ecosystem directly in Vantage, how to build multiple models simultaneously against data partitions directly in Vantage and save the models in the SQL engine, and then how to read these models and score them directly in Vantage. To review, this approach falls into user experience number 3, in which the language interpreters and corresponding Python add-on package libraries are installed on each new SQL engine node. In-database analytics are provided via Python scripts invoked through SQL and executed on every unit of parallelism. In this case, analytic task parallelization depends on data locale. What this means is the following. For row-based operations, this means that data rows are in a single unit of parallelism, such as, for example, in cases of model scoring. There are also partition-based operations, and in this case, this means that data partitions are in a single unit of parallelism, in cases of simultaneous model building. The above couple-mentioned operations are sometimes called embarrassingly parallel. Then there are also system-wide operations. These require MapReduce-style programming because, as you can see, multiple results are received from every unit of parallelism. Here are some pros and cons. Some of the benefits of this approach is that one gets out-of-the-box parallel processing for scoring and scalar operations, as well as for simultaneous model building. Another pro is that all libraries and functions are possible by means of essentially loading into Python add-on packages as you wish. And yet another pro is that this way provides an additional path to operationalization. Among the cons of this approach is that languages and libraries are installed on every node, so this is a process that one needs to go through before one can use this approach. Global operations require a MapReduce-style programming, which the programming onus on the user to implement the programming approach in some cases. Debugging may be slightly more complex because one will need to debug Python code through the Vantage interface. And finally, one needs a level of SQL coding to drive the execution of the Python scripts in the database. Let us examine Python now running in Teradata Vantage nodes. This is done by means of the script table operator object in the Vantage database. Script table operator has been available since Teradata database version 15. It pipelines the database input-output to the command line of a Linux operating system shell child process. This way, usage can be secured and limited to executing scripting languages of interest, such as Python. Now, to execute a Python script with a script table operator, there needs to be done a series of steps. The user installs their script file on Vantage via an external store procedure call. Then the user needs to execute a SQL query that calls the script table operator and invokes the script. Note that the script table operator allows for a single on clause, which means input is only accepted from a single table or view. In other words, if you desire input from multiple tables, then you will need to combine the features you want into a single other table or view. Consequently, you can then use this derived single data source with the script table operator in its on clause. Next, the script executes in a Linux fork child process. The script table operator will read your data from the standard input and will write to the standard output, and your script will run on each unit of parallelism. For the new SQL engine, these units of parallelism are called amps. So this technique provides single amp operations, which is otherwise a mapping phase. As mentioned, you get out-of-the-box parallelization for row or partition-based operations, because in the mapping phase, one gets the final results for these operation types at a single pass. However, when you deal with an all-amp operation, then each amp only provides partial results in the map phase. To produce the final answer, you need to combine the partial results from each amp in a separate reduce phase. Partial results are not combined automatically when you do in-nodes Python scripting. Instead, a nested call to the script table operator is required, where the outer call invokes a separate Python script to execute the reduce phase and combine the partial results. Let us proceed now to the Python and script demo. Let us see the demonstration use case that we will be seeing ahead. The present demo utilizes a use case which builds models to predict the propensity of a fictitious financial services customer to open a credit card account. This is done on the population of the bank's customers first as a whole, and second, by state code. In the first scenario, various features will be generated by joining and aggregating from 3 base tables, the customers, accounts, and transactions tables, into an analytic dataset, as shown in the third part of this TechBytes series. A second dataset will be built to show how Vantage table operators then can be used to simultaneously build many models based upon a partition key. Now, this partition key will be a recorded state code variable with the top 6 states this bank does business in, and another state category that will be replacing the state code indicator variables from the above-mentioned dataset that we used in a different TechBytes, the number 3 in the series. We will see 2 examples. The first example examines a model built externally to Vantage and that will be scored in Vantage. In this case, we will take a 25% sample from the first dataset that will be extracted from the database, and then a random forest model will be built on a Python client. This random forest will be then saved as a pickle file and installed back on the Vantage new SQL engine. Finally, a scoring script will be installed and executed on the Vantage SQL engine by using the script table operator to score the entire dataset. The second example examines simultaneously built multiple models based upon the state code. In this case, all operations will be done by means of the script table operator. First, we will use the script table operator with a partition by state code clause and a Python script to build a model for each one of the state codes, and the script will be executed in the Vantage new SQL engine to produce the models for each state. Then, in a second phase, a scoring script will be executed by the script table operator, which will read individual random forest models and score them for each state. And here we are from our client machine, which happens to be my laptop, and I'm just about ready to use Jupyter Notebook to determine what the dataset is that we'll be using for the fitting process to fit a random forest model. I'm starting the Jupyter Notebook, and soon after, I'm going to the actual notebook file, where now the first series of statements has to do with the packages that we'll be using in our tasks for the present demo. So a quick look shows that we're using Teradata, ML, and SQL Alchemy. These are used for transformations and wrangling. The scikit-learn Python add-on package is the provider for the random forest model that we'll be using. And we also see some usual suspects like pandas and NumPy. We'll also be using pickle and base64 in order to bundle the model and save it into a file. So let's run these statements, and also let's establish a connection to a target Vantage system as shown here. And off we went into example 1. First thing to do is to create the training dataset that we're going to be using. Quite simply, we select a quarter of a size of the analytic dataset, ADS_pi, that we created in the TechBytes Part 3 demo of this series. And what we do is we essentially transfer these data from the database over to our local machine. So there is data transfer in this step. We create a Teradata data frame out of these data that we actually just briefly show here a few rows with the head function. So we need these data here in order to fit a model. We actually need to have all the necessary data for the fitting task. We employ the random forest classifier function from the scikit-learn add-on package. And we use 500 estimators and up to 5 features in this example. This produces the object called classifier. We're going to use the classifier in conjunction with the predictor columns specified earlier here in this variable, predictor_columns, and also with the credit card account indicator, which is the actual values that we will be using in order to train the model. So we are ready essentially to fit this model by invoking the fit method of the classifier object, and we store the output into another object that we call classifier. What we want to do now is to export the model that is stored in the classifier variable and save it into a file that we can then import into the Vantage system so that we can perform scoring in database. How do we do this? First, we use the pickle package to serialize the object that contains the model. So we serialize the classifier variable. And then you see that we do not just export the outcome into a file. We further submit it into an encoding process by using the base64 package. The reason we're doing this is that if the model is only pickled, you might actually come across a pickle attribute error upon importing the simply unpickled model into the database. You can see more information in the link that is provided in the Jupyter notebook, in the notebook that is distributed with this demo. The idea is that once we actually bundle the model object by means of these two operations, then it's ready for export. You see that we essentially write model in binary format inside the output file called rfmodel_py.out. And by doing this, we have now this file saved locally on our client machine, and we're ready to proceed with the in-database scoring step. We just saw the Python code that was used on the client to create and fit a random forest model, for example 1. Let's now take a brief look over at the Python script that will be used in database for scoring this model. So this script is called strfscore.py, and I've opened up here a simple text editor where we can see what exists in this file. First of all, we start by importing some necessary libraries, Python libraries, the sys, numpy, pandas libraries, scikit-learn, pickle, and base64 are the libraries we're going to need for the tasks in example 1. Observe that importing scikit-learn, which needs to be installed in the Python installation in database, because we need to use the same library that created the model to also score it. We will see later on which specific functions we will be using from this library. For the time being, let's start by seeing how we input the data in our Python script. So the script table operator streams table data as rows into the standard input of Python. And this is what Python does here. It takes whatever it receives from its standard input as one line at a time. So with every row it receives, it actually splits the row into the column components. The standard way where the columns are separated one from the other from a script table operator is by means of a tab delimiter. So this is what we're specifying here in Python, and this is what we're doing. We're splitting the rows by virtue of this delimiter. The result is a list called line, and we append the list that each line is to a larger list that contains all of the input data. Now, it can be very possible that some of the amps on a system might carry no data from a specific table. If this is the case, then the input data will be blank. If input data is accessed and is blank later in the script, then an error will occur, and if a Python error occurs, then the script table operator will simply be aborted with the Python error. To avoid this, we take a preemptive step to exit gracefully the Python script instance on amps that carry no data by means of a sysexit call at this point. After we take care of the input, we need to actually see how to use it inside the Python script. So we have a list that we can very simply import it into a pandas data frame, as you see here in this row. But first of all, we need to know our data. This means we need to know in the columns that we receive what these columns are. So we need to know their types and hopefully their names. As you see here, we actually specify names for these columns that we also pass to the data frame. With respect to the types, we need to point out here that when Python receives data in this manner, by inputting one line at a time, then the specific variables are all of type object. Well, this may be convenient for variables that may be strings or characters, but if these variables are numeric, then we need to explicitly specify that a column of this data frame is a numeric column. This is exactly what we do here for those columns that are numeric in the input table that we're using in our script. And now I'd like to also point out even further that some of these columns may be numeric or float numbers. If this is the case, then the Teradata database typically sends out these columns formatted in a so-called scientific format. The scientific format essentially consists of one number and an exponent that describes the entire number. The only issue with this formatting is that the database tends to put a blank space in between the number and the exponent. This little trick here removes any blank that might exist so that the numeric value is interpreted correctly as a number by Python. So once we're complete with the process of interpreting the input correctly, the Python script essentially continues with the actual operations that we wanted to do. So what are we doing here? First of all, we would like to import the file with the model that we want to use for scoring. We see here that we specify through the Python script to look into a directory called tdvdb, and inside this directory we tell the Python script that it should expect to find the rfmodel_py.out file. This is a binary file, and essentially by reading its contents, Python script saves the content into this variable called classifier pklb64. What we want to do next is essentially the reverse order of steps that we took in our client Python statements when we packaged the model into a file. So what we're doing first is that we are decoding the content of that file, and then we are unserializing it with pickle to retrieve the classifier object that we initially stored in that file. Having done these steps, we are free to use the classifier object for the scoring task. Indeed, we specify first the predictor columns, as shown here, and then we apply the predict_proba method of the classifier object to the he_test variable that has the predictor columns. The output is essentially the scoring results that we're looking for. So each row will produce the corresponding customer ID and the output of the predict_proba method that scores the specific customer on the basis of the fitted random forest model. So what are the values that we receive? It's the probability that the customer will open a new credit card account being 0, the probability that the customer will open a new credit card account, and then the actual value stored in the credit card account indicator column. And by this, we complete the presentation of the scoring Python script that will be used with script table operator in database. And the next thing to see is now how we're going to put this together alongside with the model inside the database and how we're going to execute the script table operator with those. To do this, we will need a SQL script that is essentially a script that we will execute within a SQL IDE. In our case, we're using Teradata Studio. What you're seeing here is a connection that I've established to the target Vantage system. And I've opened up here the TechBytes part5demo.sql, which is a SQL script with all the statements that we will need for the two examples. So let's focus first on the first example and see what we have here. The script starts with a specification of the default database since we're operating inside the tdvdb database. The next thing that we need to specify is the search UIFDB path. This is essentially the database path that we're telling the script table operator to account for in order to find within this path the user installed functions. So this is what the 3 letters UIF here stand for. And by specifying this path, we can expect that Python scripts will find in a directory named as such the scripts and any other objects we upload into the database for it. The next step is to simply just now upload what we have. We would like to upload first the model file, and we start by the installation function that is used for this purpose. We specifically invoke the external store procedure called install file, as you see here in this row. So this is a function that essentially goes to a specified location on the client file system, in this case, in this scenario, where we have stored the random forest model file, and essentially it transfers from this location over to the target DB path, search UIFDB path, the file that we want to transfer over to the file that we want to upload over to the Vantage database. Now, if you have different versions of a file, or if you have a latest version that you would like to use, then updating is not taking place automatically. One will need to remove previous versions of a file and then install the latest one as shown here. In our case, earlier on, I actually did use an earlier version of that model, so I will be removing it and then installing the latest one from the location that I specify over here. I will execute these two statements. It's just that the actual model file is a little bit on the hefty side, weighing at about 15 megabytes. It's not too large, but it's large enough for my connection to take a few minutes until the upload has taken place. So I'm going to execute these two statements, and we will resume in a bit when the upload is complete. So a few minutes went by in between, and now the model has been uploaded, the model file, and exists in the target Vantage system. The next thing that we would like to do is, in a similar way, upload the scoring script that we reviewed a few moments earlier. And for this reason, we also need to use the sysuf install file, XSP. If you have previously installed another version of the same script, you need to first remove it and install anew the latest version before you actually can use the script, the updated version of the script within the database. Let me run these two statements. As you see, the upload in this case was much faster. And then the next thing that we need to do is to simply invoke the script table operator with the Python now 3 interpreter in the command line. And as an argument, I'm using the Python scoring script. Please note that I need to invoke it from the location that was installed on the Vantage NewSQL engine, and you see that the location in the database is actually under the sysuifdb path that I specified earlier on. What are we doing here? We want to select all columns from the ADS_py, so we're going to be scoring all of the rows in this table. This table is spread all around the system, but all that we need to do on each AMP is to essentially run an instance of our Python script on each AMP and score each one and every row that exists on this AMP. So we expect essentially a parallelization of this task and a speed up based on the amount of amps, that our Vantage system has. What do? Essentially, we're returning back the results as we saw in the script, which will be the 4 columns, the customer ID, the probability of 0, the probability of 1, and the actual value. And these will be returned, as you see, once the script runs, these will be returned as columns as output, direct output from the script table operator. We see that we get about 10,000 rows back, and we're just being asked here just to get a sample of those 2,000 for the purpose of what we're doing here. Yes, we only just need to review the results, and we see randomly chosen result output rows from our scoring task. And these are the results shown in the Teradata results set viewer, as you see down below. Now, these results can essentially be saved into a table, so these results can be persisted if you wrap this call to the script table operator by means of create table as. And we will see this in the following example too. But for the time being, this operation produces the results that we were looking for, and we are essentially done with example 1. We will be continuing with example 2 in the following. And here we are where we left our Jupyter notebook earlier on after the completion of example 1. Let's look into how we're going to set things up for example 2. We're going back into our notebook because here is where we would like to use Teradata package to transform and wrangle our input tables in Vantage in a way that we can actually create now the analytic data set for example 2. I remind you, in the example 2, what we want to do is fit multiple models and score them in database with a script table operator using Python scripts. So let's get started here and see how we can produce first the analytic data set that we will need for these operations. First, nothing has changed from the tasks that we performed before, so I'm already still connected over to the Vantage system that I used for example 1. And over here, the specific code for example 2 first starts with a definition of a utility function that I have. If you remember from our demo 3 earlier with Teradata, we use this function so that we can replace essentially nulls in a column with zeros. The next thing that I'm doing is that I'm start running also these segments as we move on. The next thing that we would like to do is to create Teradata data frames for the basic input tables that we'll be using, the customer accounts and transactions tables, which reside in the Vantage SQL engine. And the data pre-processing will be quite similar to what we saw in demo 3. For this reason, we will not be going into too much detail. However, I will be pointing out the differences compared to the operations that we did in demo 3. So in this specific demo 5, what we want to do is to create a new column out of the indicator variables for the different states. So this new column will be called state code, and essentially it will be nothing more than the state name, if it is one of those 6 most populous for this bank states, namely California, New York, Texas, Illinois, Arizona, and Ohio, and all other customers from all other states will be added in one single category that we will call other, as in other state. So let us run the segment. And by running these statements, essentially what we're doing is that we're creating a new column projection to use for the customer data set. We save this into a data frame, and you actually now see in the results the new state code column, where, for example, for the first row, it happens to be other. the value is other because if we go under the state code, it's Colorado, all right? So this is not one of the 6 columns that we retain their name in the state code. Anything other than Texas, California, and a few more that we mentioned will be classified under the keyword other. The next thing that we would like to do is to get the account table information and create a column projection like we saw in demo 3. This step is completed and we have now the account data frame. We want to do the same thing also for the transactions input table. We create a column projection for that. It's already done. We're continuing now with joining the account and transactions data frames in the step that leads us to essentially bring together all of the different data frames into the final analytic data set that we want. This operation is also done. We also need to perform left outer join of the account transactions with the customer data frame on the customer ID variable. Let's run this statement as well. You see here that we're including now the customer state code expression for the state code column. This one is done as well. It seems that we have all the joins that we need for our new ADS_PI2 analytic data set. And finally, we only need to aggregate these values by customer ID and roll them up. And this will produce the ADS_PI2 dataset. We see that in the same block of statements, we also save the data frame now as a table in the new SQL engine of our Vantage system under the database, under the schema TDVDB as specified here. So one more step that we need to do is to take our new analytic dataset and create training and testing datasets. We again do a 60-40 split by means of this SQL call. Let's just execute this one. So we use a 60% sample as a training dataset, and we store it in a dedicated table on the database, the multimodal train_pi. And we act also accordingly for the testing scoring dataset that we save on the database under the table name multimodal test_pi. And this is the end of our session. We used essentially Teradata ML to do all the wrangling that we needed to do to create our new analytic dataset and training and testing tables. Now we will be doing all the analytical part. Inside the database, we will be creating models for each one of the 7 state categories under the state code variable, and then subsequently we will be scoring with those models the testing dataset in the steps that will follow. For now, within the Jupyter notebook that we have, we only need to finish up our session, and we do this by cleaning up. Essentially, we execute the remove_context Teradata ML method, and this means that we are good to go and continue. So the next thing that we would like to do past this point is to review now the Python script for multiple model fitting and the Python script for multiple model scoring that we will be using in the database like we did before with example 1. So let me just jump here over to my text editor, and I still have the scoring script here. Let's jump into the random forest fit multiple model script, Python script. This is quite similar in much of the setup that it involves. It's quite similar to what we saw before. For example, again, this script is expected to receive as input the table that we saw, the table that will have the fitting data. So again, we read these data from the database in the specific format with the tab delimiter. Each row is read in as a string line. The string is split by means of this delimiter. We then take each one of these rows, and since Python interprets those as object type, we need to specify which ones of those are numeric type and convert them explicitly so to numeric type elements. And then the next thing that we need to do is to do our model fitting. What do we have here? We need to specify the predictor columns that we will need for our model fitting, for our random forest model fitting, and see now that we invoke again for random forest fitting the random forest classifier. Only in this case, we're doing this from within database. And now the random forest classifier will essentially operate on the instance of this script that will be running under every AMP, under every processing unit. And guess what? Since we're using partitioning by the state code, and we only have 7 of those partitions, there will be only 7 amps, okay, that will be having data that we would like to use to create models. So we expect to get back 7 of those models. What kind of models will we be getting? Well, we use the random forest classifier that returns back its result that we call it classifier. We define these variables x and y based on the predictor columns in the data frame and the credit card account indicator here. And then we invoke the fit method for the classifier object that gives us, essentially, that should give us on each and every AMP the fitted model that we expect to receive. Same story, we get back the models, and what we would like to do to use them at a later point would be to actually pickle them so that we can serialize them and store them. And because of what we saw earlier in the example, an additional step instead of just serialization is also encoding those models. And then we will have the result that we specify to send it out. And what kind of result do we want to send out as an output? What we are saying here is that we would like to print the specific state now for which we are applying this model and the model itself. These are separated by the delimiter, and that will be the output of the fitting model. If we go next to the scoring part, the scoring part is not that much different from the scoring that we did in example 1. I'm only going to show the differences here. The difference has to do first with the way that the data are read. We're not now receiving data that are just the scoring data. We also need to read the model itself. You will see that the way that we are sending this information to the present script, we will be having essentially a table that is streamed to the present script, and there will be another column on the right-hand side. This column, on its first row, it will contain the model. This is what we're doing here. We are reading now the lines in a way that the first line that comes in isolates the last column value, which is the model that we want to use for scoring. And then, up until all the input that is being streamed is depleted, just keep reading the lines and storing them like we've seen before. And by the way, if we're one of those AMPs that have no partitions that refer to one of the 7 states that we're dealing with, then simply just exit in a graceful way and let the other AMPs that have data do their job fine. So once we have the information read in here, we simply do the same story like we did before in the previous scoring task. So we decode the information and we unserialize it. Now you see this extra step that I'm taking here, where I'm essentially splitting the information that comes from the encoder. I'm doing this because if you actually see the model in its form as a variable in Python, Python 3 simply stores it in a specific way that splits the useful part that we need on the right-hand side from some other information on the left-hand side with a single quote, as you see here. For this reason, this is a trick that we do essentially to retrieve the actual model information that we want and nothing more that is being created by Python. Once we have this information here, we are ready to score the data that we have streamed into our data frame earlier. We specify the predictor columns. We use the predict_proba method for the classifier that we have previously stored for our random forest model. And then simply, we just send out the results. What are the results in this case? We want to send out subsequent continuous rows of our data frame, where we'll be sending the customer ID, the state code value, the probability for 0, the probability that the credit card account will be opened, and then the actual value in the end with the indicator. Having seen this and that, let us jump straight into Teradata Studio environment, where we will actually execute now the multiple model fitting and scoring scripts. Here's where we left things earlier on. We're in example 2. What do we need to do? First, do the fitting part. Simply install the multiple model fit script, which is done. And then we would like to create now a storage object for the models that we will create when we run the fitting script inside the database. So this object is nothing else but a table, okay? Because you saw what we're doing. We're going to be executing a fitting script, and the output are essentially going to be rows, 1 row from each AMP, and we expect to have 7 rows that will contain the 7 models that we want, 1 from each AMP, because we have 7 categories that we would like to fit models to. So if you already happen to have a table that you got from a previous execution of that script, you will probably need to drop it. Otherwise, there will be an error, as is in the case that I'm showing you here. So I had previously run the script. I already have a table. So I'm just dropping it before I execute the fitting script again. And here you see essentially the call to the script table operator. It's very similar to the call that we did before in example 1. Okay, in this case, what we have is a different input. All right, we use the input from the multi-model train actually _pi, and then we need to partition our input by the state code, which we have specified here as S code. We then run the multiple model fit script, and we expect, if you remember, we expect to receive back the state code and also a character large object, which will be the model that we receive in a serialized and encoded form. Now, to persist this information, we wrap the call to the script table operator within a create table statement. So we create a table that will hold the models as this call to the script table operator, right? Let's see what we get out of this. Let's execute that statement. And the execution is done. So for example, if I would like to go and see what this table contains, I could very easily try and do something like select all from this table. So let's see what we have here. And I get a message here that I have a character large object. So I'm being asked, what would I like to do with this? Would I like to save it? Would I like to see it? I'm just skipping all that. I prefer to not show or save through Teradata Studio what a large object is. And this is what we're getting back. As you see, I only have 7 rows in this table. I have the state code in the first column, which is the 7 categories. So the 6 states and the other category that we specified earlier. And on the right-hand side, you actually get to see a snippet of the model. Check this out. Python saves the model in a serialized format, and it's also encoded here. And as you see, it starts with the letter B and a single quote. The B stands for binary. And the actual model information follows the single quote that you see here, hence the trick that we applied earlier in our Python scoring script. Speaking of which, now that we have the models, let's just proceed and score them. What do I need to do? First, I need to load the scoring script into the database. Just did. And the next thing is now that I would very much like to essentially run this query here. This time we're getting the scoring data from multi-model test _pi, as you see here. And there is a small level of complexity here in the on statement. Remember, I'm not just sending now the data that I wish to score, I also need to provide the table. So this is where I'm sending essentially all the columns of the scoring data set, and in the first row of what I'm sending, I would also like to provide the model for the specific state code. And then I would like to order all of my results by the row number. And this is very critical because, remember, my Python scoring script expects to find the model in the first row. So the rows, as I'm sending out those to the Python script in this script table operator call, the rows need to be ordered. So without further ado, let's go and run this code snippet as well. So until we get the results from the 7 apps that actually have the information about these state codes and the models, let us briefly review what we expect to see. As you saw in the Python scoring script, we expect to receive back an integer, which is the customer ID, the state code, the probability that the customer will not open up a credit card account, the probability that the customer will open a new credit card account, and the actual value. And we see that now we have about 4,000 rows. That's the 40% testing subset, okay, of our analytical dataset, of our initial analytical dataset. Let's just get to see a sample of up to 2,000 rows. That is the default for Teradata Studio. So this is what we essentially have. Customer ID, state code, probability for no and yes, and the actual value. For example, you see that in the first row, we're actually quite certain that the customer will open up a new credit card account, and so forth. You get to see the results for the rest of the rows. So essentially, this concludes the task for our second example as well. This presentation concludes the fifth and final part of the TechBytes series using R and Python with Teradata Vantage. We've showed the Python and table operators demo. Thank you very much for your attention.